Potbelly Hill, a mound located on the arid hills in southeastern Turkey, was long considered a sacred mound. On a clear day, the breathtaking view from the hill extends to the very horizon. However, in the mid-20th century, archaeologists realized that Potbelly Hill was not just a good vantage point. The remains of an ancient settlement were buried here. But mistakenly not noticing anything remarkable, archaeologists did not conduct excavations and moved on. Only in 1994, local residents told German archaeologist Klaus Schmidt about this mound. With the help of local farmers, he took the initiative and began excavations. Soon, Schmidt realized that these large T-shaped stones were not tombstones, but the upper parts of enormous megaliths. Further excavations revealed a massive complex, including towering T-shaped pillars, long arched pathways, and concentric circles of impressive stone walls. But this was not the biggest surprise. When archaeologists were able to date the structure, its age astonished them. The complex was over 10,000 years old. Potbelly Hill, known as Göbekli Tepe in Turkish, turned out to be one of the oldest structures ever built by humans. The complex was constructed at the end of the last ice age, during humanity's transition from hunting and gathering to a settled way of life, long before the Egyptians, Jews, Hindus, and Buddhists. To this day, archaeologists do not know the true purpose of this structure. Nevertheless, the Göbekli Tepe complex was of vital importance to the people who built it. For some reason, it remained lost and forgotten for millennia. Thousands of years of human history, hundreds of cultures, and dozens of major civilizations rose and fell in this region, never considering it as anything more than an old hill. The Göbekli Tepe complex serves as a cornerstone of our current understanding of the development of human civilization. Without it, our past would be even more mysterious. Yet it was constructed only about 10,000 years ago. In the grand timescale of our planet's age, approximately 4.5 billion years, this is a very short span. As we delve deeper into the past, the story of our origin becomes even darker. Using fossilized fragments scattered around the world, we piece together our history, the history of human evolution. Additionally, according to archaeologists' estimates, we have fossil evidence for only about 1% of all the species that have ever lived, and this accounts only for life on our planet Earth. Just a few decades ago, with the help of various probes, telescopes, and technologies, we only began to explore the farther reaches of space. However, a significant portion of the universe remains unknown and unmapped. What secrets await us out there? How far can we trace not only our own origins in life on Earth, but also life in the universe? Like Göbekli Tepe on Earth, what ancient monuments of life await us in the depths of interstellar space? Are we one of the first generations or one of the last in a long line of births, lives, and deaths? And can we identify extraterrestrial life, even if it is staring right at us? To identify life, we must give it a definition, and current scientific literature contains over 200 different definitions. The classification scheme is based on the idea that life possesses three distinct properties. First, life must have the ability to store information. Regardless of the means, life must encode information about its current state. It must also store information about its own traits and characteristics, as well as the information necessary for various processes. Second, life must be capable of catalyzing reactions. It should have the ability to interact with its environment, react to it, and generate its own responses. These reactions enable life to acquire, store, and expend energy. They also allow life to respond to signals and threats. Furthermore, these reactions enable life to create new structures. Lastly, and no less importantly, what distinguishes life from non-life is the ability to reproduce itself. Life must have the capability to create copies of itself, and these copies must closely resemble the original. The combination of these three factors is what allows life to exist. The renowned physicist Erwin Schrödinger was the first to define the fundamental principles of life from a physical perspective, suggesting that the storage, use, and transmission of information are of primary importance. The information stored in life provides the instructions necessary to catalyze reactions, and some of these reactions include the ability of life to reproduce itself. This way, life can continue and perform all the activities we typically associate with it. It can move, eat, defend itself, send and receive signals, and most importantly, reproduce. This complete cycle also allows life to undergo natural selection. The pressure from the surrounding environment acts on the information passed from one generation to another, selecting certain traits as useful for survival and ignoring others. This in itself implies another definition of life. Life is capable of evolution. And on modern-day Earth, we can see a vivid example of this definition, ourselves being a prime example. We have DNA for storing information. We have proteins that catalyze reactions. We have RNA that acts as a translator of the information stored in our DNA. Finally, our DNA, through RNA, provides information for the creation of proteins that continue to produce copies of our DNA, passing on our genetic heritage from one generation to the next. With confidence, we can assume that all life in the universe adheres to this fundamental definition. If it were not the case, it would be very challenging for us to identify living organisms as living. But what about the origin of life on early Earth? At some point, a collection of chemical processes transitioned from non-life to life, and this boundary was likely blurred. The modern DNA-RNA protein triad could not have existed in early life because if you remove one of them, the life cycle cannot be completed. So early life must have been simpler. One hypothesis suggests that early life consisted solely of RNA strands. These earliest forms of life would have been entirely different from the life we know today. Therefore, contemplating this strange early life leads us back to the question, can we recognize extraterrestrial life at all? Some aspects of early earthly life that we could still find common might help us. Early life used liquid water as a solvent, and solvents are crucial for our understanding of life. Life on Earth uses a mixture of complex molecules to live, store information, catalyze reactions, and more. These molecules need a place where they won't be instantly destroyed, and water is stable enough without sudden and critical temperature fluctuations for these purposes. Additionally, water can bond with many other molecules and dissolve those you don't need. Although the first life on Earth could have been extremophiles, such as bacteria that can survive in deep-sea hydrothermal vents, they all existed within a wide range of Earth's climatic conditions. Early life also used the same elements we are familiar with today. Carbon is exceptionally convenient because it can bond with itself and other elements, allowing it to form large and sturdy structures. Oxygen is excellent for participating in chemical reactions, making it a useful tool for storing and subsequently using energy. Phosphorus, nitrogen, and hydrogen also play crucial roles, especially in building DNA and RNA. So early life might not have been so alien after all, the same solvent and the same building blocks. But all of this is on Earth. Everything beyond Earth is an entirely different story. Perhaps what happened on our planet is universal, and nearly all forms of life in the universe require the same basic ingredients: water, carbon, starlight, and so on. Or maybe not. After all, we have only one such planet for now. In 1952, a graduate student at the University of Chicago named Stanley Miller conducted an experiment. This experiment was very simple. Miller took a flask of water and added a mixture of methane, ammonia, and hydrogen to it. Then he passed an electric spark through the flask. First, nothing happened, but after a day, the mixture turned pale pink. Within a week, the liquid in the flask became dark red. Using a chromatograph, Miller determined which new molecules had appeared inside the flask. The results were astonishing. Glycine, alpha-alanine, beta-alanine, aspartic acid, alpha and aminobutyric acid. These were amino acids, the building blocks of RNA and DNA, the foundations of the chemistry of life. Miller's experiment shook the world. Before this, philosophers, theologians, and scientists had only vague ideas about how life could have originated on Earth. Miller's experiment showed how a mixture of simple molecules could create the basis for the rich organic chemistry of life. The starting materials for the experiment, water, methane, ammonia, and hydrogen, are among the most common molecules in the universe and are composed of carbon, oxygen, hydrogen, and nitrogen. The outputs were amino acids, which were much more diverse and complex complexes of the same basic elements. Amino acids play a central foundational role in biochemistry. Our DNA encodes information about 20 of them, and combinations of amino acids give rise to our protein structures and all life on Earth. The experiment simulated hypothetical conditions of early Earth, a warm mixture of so-called prebiotic molecules. The spark simulated the impact of lightning in a primordial pool, triggering a chemical transformation that would one day lead to the life we know. Further studies of the original experiment showed that Miller had created even more amino acids, but at the time, the technology didn't allow for their detection. These new amino acids included variants not used by life on Earth. For some reason, our planet settled on this group of 20, although many more options were available. Miller's experiment demonstrates one link in the chain of creating life as we know it. All that's needed is a prebiotic mixture of elements under the right conditions. To find the earliest time when life could have emerged, you need to be able to identify the correct mixture of elements and the right conditions. But where could that be in the universe? Of course, one place we can be sure of is right here, our planet. Earth has abundant water supplies, and our planet is protected by a thick but not too dense atmospheric layer. Additionally, our planet is located in the so-called habitable zone of the Sun. The habitable zone is the region around a star where the temperature is just right. Any closer, and the water would evaporate, as on Venus. Any farther, and the water would freeze, as on Mars. Every star has its own habitable zone, and the location and size of this zone depend on the nature of the star. For example, small dwarf stars have habitable zones almost adjacent to their surface. Giant stars have habitable zones stretching hundreds of millions of kilometers. The Sun's habitable zone starts just beyond Venus's orbit and extends to Mars's orbit. But of these three worlds, currently only Earth has liquid water. So, from this small example, we can conclude that the conditions for life as we know it are very strict. In 2003, a group of astronomers discovered glycine, the simplest of amino acids, in several giant molecular clouds. These clouds are regions in galaxies where stars and planetary systems are formed, so it is also possible that amino acids appeared on Earth during its formation in the very beginning. In addition to amino acids, astronomers have also detected various organic compounds in our galaxy, in many other galaxies, and even in distant quasars. These quasars, shown only in the early universe, suggesting that the basic chemistry of life has existed in the universe for a very long time. But even that is not the true beginning. All of this chemistry had to come from somewhere. Molecules are formed from elements through various processes across the universe. Almost all of the elements in the periodic table are created in a process known as stellar nucleosynthesis. It is known that the first stars appeared about 100 million years after the Big Bang. We also know, based on observations from space telescopes, that galaxies were fully formed around 500 million years after the Big Bang. There was a time before this, when our universe was about 10 to 15 million years old, when the cosmic microwave background filled the universe with radiation at room temperature. But this was long before the formation of rocky planets, or even water. The first opportunity for life as we know it, floating in oceans of liquid water on a rocky planet orbiting a stable star, could have arisen between 100 and 500 million years after the Big Bang. Our solar system, however, formed 9 billion years later, so it is safe to assume that Earth was not the first opportunity for life to arise in our universe. But of course, this applies to life as we know it, not to life that we can imagine. Earth isn't all that special of a planet. Yes, it has liquid water on its surface, a mild climate, a rich soup of organic materials, and an abundant and stable energy source. We have no evidence of these conditions leading to life anywhere else in the solar system, let alone the galaxy. And yet, the universe is vast. Our galaxy, the Milky Way, contains about 400 billion stars. In the observable universe, there are potentially around 2 trillion galaxies, and in physics, nothing happens just once. Either nature forbids it, and it never occurs, or it allows it. And the universe is large enough to accommodate many occurrences of even the rarest phenomenon. That's why we have no reason to believe that life is so rare in the universe. Our world is just one rocky planet, orbiting one unremarkable star. If life originated here, logic suggests it must be some common trait of the universe, which means it could have originated elsewhere too. Moreover, the universe isn't just enormous, it's ancient. And that means life, similar to that on Earth, could have emerged as early as 100 million years after the birth of the universe itself, since the cosmos is now nearly 4 times older. Life on Earth appeared as soon as the Earth's crust cooled and the oceans formed, almost 4 billion years ago. A simple glance at the geological history of our planet illustrates the risks associated with life, as at least 5 times, life was nearly wiped off the face of the Earth. But each time, like a phoenix, it rose from the ashes. Life is like a virus, capable of going dormant and traveling through the universe for millions or perhaps even billions of years on comets and asteroids until it lands on a planet with favorable conditions where it begins to reproduce and evolve. And if that's the case, it's quite possible that we could spread not only throughout the solar system, but also across the galaxy, overcoming vast distances. Perhaps we as a species could live for millions of years or even longer to remain a technologically advanced civilization. And maybe then, in the distant future, we might meet intelligent brothers who are far older than us. But the problem is that all of this is insignificant on the cosmic scale. The universe is 13.8 billion years old, and our home galaxy is just one among trillions of others. Eventually, some limit will be reached, and we will simply go extinct, leaving behind a legacy in space. But as we've learned, one form of life is always replaced by another. So, over nearly 14 billion years, and among trillions of galaxies, other intelligent species have arisen, are living, and are spreading, but vast space and time separate us. And perhaps they are made entirely of antimatter, living parallel to us, but they live significantly longer than we do. Maybe that's why our loudest radio signals are just whispers in the background, and our brightest beacons flicker like candles with a dim light. But whatever the case, life never stands still. It evolves, which means our technologies are also developing, and sooner or later, we will find answers to all our questions. In the year 2020, we have images of black holes, breathtaking panoramas of the Milky Way, detailed snapshots of distant galaxies, and the stunning James Webb Telescope is getting ready for launch. However, 30 to 35 years ago, everything was so different that such news would likely have shocked engineers and scientists. If we had the opportunity to call a scientist directly in the year 1985 and ask a couple of interesting questions, like the existence of planets around other stars, they would probably say that it's likely, but not certain. Now, it's not 1985 anymore, and thanks to new methods and modern technology, today we have thousands of stars in our own galaxy that have their own solar systems. We have discovered planets of various sizes, characteristics, and masses at various distances from their stars. We have planets even larger than Jupiter that orbit stars in less than 48 hours, and NASA's Kepler mission has made a huge contribution to the search for such planets. It's no longer breaking news that Earth-like planets are being discovered. But let's reason more simply, as each of us has a specific idea of what intelligent life is, and each of us has an idea of the conditions under which this life can exist. Let's imagine a simple analogy: intelligent life in the universe and an ordinary tree. If I ask you whether a tree can grow inside an iron box, or whether it can exist there, you would accurately say no, because you understand that a tree requires certain ingredients, such as soil, fresh air, sunlight, and some nutrients. In fact, the logic is such that we just need to find the same things that exist on Earth, and then we will surely find life. This is how we think now. But consider the fact that you are not Mickey, defining the concept of life only like the one on our Earth, because you haven't seen any other life, heard nothing about it, and are unlikely to hear about it in the near future, and maybe never. So, if we set ourselves the question of searching or pondering whether intelligent life exists in the universe, it's important to understand correctly what form or type of life we want to find. It could be similar to us or something entirely different. Of course, the simplest ways to answer such a question are to apply mathematics, probability theory, and real observations. But in that case, once again, we will be looking for life solely similar to ours. Remember that tree I mentioned. The key point is that we know what it looks like and what conditions it needs. Therefore, we can easily predict where a tree can grow and where it's extremely impossible. If you want a simple answer to the question of whether life exists somewhere in the universe besides us, I will say that it's 100% likely, given what we consider as life. I know this is my personal opinion, but I will try to explain why I'm confident about it. I present to you 10 amazing places in the universe with a full potential for the formation of life. It's not a secret that soon after the formation of our planet, life appeared on Earth and is progressing today. Of course, it's possible that earthly life didn't originate on Earth, but came from somewhere else through natural cosmic processes. And in this conversation, it doesn't matter whether it originated here or somewhere else. What's important is that the basic ingredients for life exist everywhere we look. For example, consider a dozen places where these ingredients are most frequently found. First, there's gas ejected from young objects, like the Herbig-Haro objects, which contain various organic molecules. Another example is protoplanetary disks, where there's a vast diversity of complex compounds and organic molecules. For instance, there's the protoplanetary disk around the young star, H.L. Tauri, photographed by ALMA. The gap in the disk indicates the presence of new planets, and spectroscopic measurements reveal a large variety of carbon-containing compounds, which are essential for life. Even on Pluto, there's thallium and methane, and a rich organic haze. Even in the images from the New Horizons mission, atmospheric hazes are clearly visible and measured for the content of several carbon-containing compounds. Nebulae illuminated by a bright young star are rich in numerous complex carbon compounds, are reflective nebulae for containing a wide variety of complex organic molecules. Reflective nebulae are common sources of raw materials for life. By the way, inside meteorites, there are numerous amino acids and proteins, some of which are not found in nature on Earth. For example, the Murchison meteorite that fell in Australia in the 20th century. The fact that there are more than 80 unique types of amino acids suggests that basic ingredients for life, or even life itself, could have formed differently somewhere else in the universe, perhaps even on a planet that is not orbiting a sun-like star. The gas in the galactic center includes vital compounds. Idol's Pharma is responsible for the recognizable aroma of raspberries, though Russian scientists don't acknowledge this. For example, the wave image of the galactic center shows us stars and gas, with a tremendous amount of material, including heavy elements and organic compounds, which are essential precursors for life. And this is the molecular cloud of Taurus, where new stars are formed. It contains dozens of organic substances, including carbon chains. For example, in the image, the brighter areas in red have the highest density and active star formation, while the blue areas correspond to cooler, less dense regions. However, organic molecules are found in both places. Planetary nebulae formed by the death of sun-like stars contain more than 20 molecular species, including fullerenes. These are abundant on Earth. Interestingly, fullerenes and complex organic compounds can form rapidly and survive to a significant extent during the evolution of any star. Nitrogen, hydrogen, and oxygen are strongly highlighted in this planetary nebula. Different colors clearly indicate the locations of various elements, which are separated from each other. Complex molecules, including fullerenes containing 60 carbon atoms each, have been detected in these planetary nebulae. And you don't have to go far. Sedimentary rocks on Mars contain rich organic compounds, some of which are over 3 billion years old. For example, the American NASA rover on Mars discovered ancient organic molecules embedded in sedimentary rock deposits that have existed for billions of years. They contain carbon and sulfur and could be associated with life beyond Earth. Over the past decades, our knowledge of the existence of planets around other stars has grown to incredible numbers. The number of known exoplanets has changed from a few dozen to more than 1,000 officially confirmed objects. Therefore, now we are confident that exoplanets can come in various sizes, be at different distances around all types of stars, have different masses and characteristics, and these are real data. It's not surprising that against the backdrop of such acquired knowledge, various questions arise in our minds, seemingly logical at first glance. For instance, when will we find the first inhabited planet beyond the solar system? Or what does habitability on a planet actually mean? Do planets exist that closely resemble our home, Earth? All this is done in order to understand where else life might exist. However, the thing is, the more we learn, the more we realize that being interested in and searching for a planet similar to ours with the presence of life is very inappropriate. This is because the universe is incredibly diverse, and places with the presence of life might not be anything like Earth. Perhaps these conditions could be even better or completely different from what we can imagine. We'll talk about why the assumption that a planet similar to Earth is a requirement for the existence of life is misleading. Having only one successful example, the planet we inhabit, leads to this kind of misconception. If we look at our solar system with all its planets and moons surrounding us, it becomes obvious that Earth is something unique. Only we know why we consider it special. Maybe it's because Earth is the known world where life originated, was sustained, developed, and flourished. It transformed the biosphere and eventually became complex, diverse, intelligent, and technologically advanced. Scientists are looking for conditions that resemble those Earth has experienced and continues to experience. They assume that a potentially habitable planet with life must be similar to Earth. But this is where they make a crucial mistake, because these assumptions imply that the conditions our Earth has faced are the most favorable for the desired outcome of life. However, as we learn more about the universe and the solar system, we have solid grounds to challenge such an assumption. There are 5 key points we need to consider. The first thing that comes to mind is a planet the size of Earth. After all, it seems like the ideal size for life. If we're too large, we might be enveloped in a massive hydrogen or helium envelope, like Neptune or Uranus. And if we're too small, we might struggle to maintain our atmosphere, like Mars or Mercury. Hence, the conclusion is that Earth's size is the way to life, right? Saturn's moon Titan is smaller than Mars, yet it maintains a denser atmosphere than even Earth. Moons like Europa, a large watery moon of Jupiter, might have ideal conditions for subaquatic oceanic life. Isn't it paradoxical and intriguing? These typical examples are right here in our very own solar system, yet they don't remind us that the potential for life exists in many worlds of vastly different sizes. The size of Earth is not a special prerequisite for life to form. The second point worth mentioning is the so-called habitable zone. If we have a planet the size of Earth with an atmosphere, we need to place it in a favorable location around its parent star to have the necessary temperature for life to initiate. This also seems logical. However, the thing is, a planet much farther from its star can have a denser atmosphere, leading to moderate conditions. A planet with a lower albedo or specific cloud cover properties might be closer to its parent star and still have moderate conditions. Hot planets could thrive in their upper atmospheric layers, while cooler planets could harbor life beneath ice. The habitable zone is a fifth-place starting point, and science has progressed to a point where this simplistic definition is no longer useful. The third point is the ability of a sun-like star. The majority of stars in the universe are red dwarfs, low-mass stars that burn slowly and steadily, in contrast to only about 20% of stars that share the fate of the sun, burning for billions of years before becoming red giants and ending as planetary nebulae. Although red dwarfs mostly have a low mass and undergo very slow nuclear reactions, emitting little light, many planets orbiting them are locked by tidal forces. However, this doesn't mean these conditions impede the formation of life. There is a risk of cutting off unnecessary possibilities by limiting ourselves to our primary assumption. While it's more likely that life in red dwarf systems may be challenging, until we truly start conducting a census of the universe's population, measuring the atmospheric properties of all available planets, we cannot make a comprehensive conclusion that life in these systems doesn't exist at all. The fourth point is that life regulates its own biosphere. This is another key question for which we don't have an exhaustive answer. Can a planet, initially uninhabited and considering only physical and chemical processes, transform and remain habitable during the early stages of simple life? We know Earth has many feedback mechanisms, and we also know that significant external changes might result in only minor changes within our biosphere. Does having simple, early forms of life hold the key to the development of stable, long-lasting life on a planet? After all, the conditions for its origin are more realistic and favorable. If this is the case, we cannot significantly understand what makes a planet potentially suitable for life until we gain a more complete understanding of this matter. The fifth point is the significance of heavy elements. The very first generation of stars consisted mostly of hydrogen and helium. In our solar system, about 2% of the total mass of all objects consists of heavier elements such as oxygen, carbon, nitrogen, and other essential life elements. Stars with a sufficient amount of heavy elements cannot form rocky planets, nor the simple molecules necessary for life. However, where do we draw this line? Can a solar system made up of half heavy elements be sufficient for life to form? And what if the percentage is 10, or even just 1? Or perhaps it could be as high as 500% in the opposite direction. Therefore, regardless of a specific threshold, we lack a clear understanding of whether we are a rarity in the universe or a typical outcome of probability theory. These are just some of the open questions that hinder our comprehension of a planet similar to Earth. An intriguing fact is that the universe plays with numbers. Consider our observations, for example, within the Milky Way. There are approximately 10 billion Earth-sized planets orbiting within the habitable zone of stars similar to our Sun in terms of temperature and mass. A significant portion of different systems have a comparable concentration of heavy elements to our solar system, indicating that a vast number of exoplanets could potentially be candidates for Earth-like conditions. However, there are also numerous exoplanets of a different type that do not meet these criteria. Such planets are far more abundant than those we naively describe as being similar to our own. The quest for Earth-like planets may lead us to overlook many planets in the galaxy where life may have already originated and begun to thrive. In order to discover something, a more unbiased approach would be to observe everything within our capability. Of course, it's easy to argue that Earth possesses all the conditions for life, which should at least allow us to consider the possibility that planets with similar conditions could also harbor life. So let's start by acknowledging the imperfections in our search for life on exoplanets. It's this kind of thinking that ensures we will obtain biased results in any search we conduct. But if, before the search even begins, we simply decide that life cannot exist around red dwarfs, that exoplanets or moons of incorrect sizes or at incorrect distances from their stars will never form life, or that stars with insufficient heavy elements cannot support life-bearing planets, we risk not only overlooking numerous cases of life in the universe, but also the overwhelming majority of habitable planets. The thing is, nearly 80% of the stars in the galaxy are low-mass stars, and there may well be more worlds the size of Mars or Liverpool, smaller than Earth, orbiting these stars than Earth-sized worlds. There's probably a multitude of atmospheric conditions that can permit life at various orbital distances. There might even be more exomoons of significant size around gas-rich massive exoplanets than Earth-sized exoplanets. So how tempting it is to assume that if we have one successful example like Earth, we should seek examples that mimic that known success. However, this is an incorrect scientific approach. The correct approach is to seek as many plausible worlds as possible that could include these conditions, not limiting ourselves to only Earth-like conditions. It's entirely possible that most planets with conditions similar to Earth's are actually inhospitable to life. Meanwhile, many planets with conditions different from ours may be even more suitable for life. Until precise studies reveal the answer, presuming that Earth 2.0 has a precise scientific basis is speculative at best. The story of how the universe became what we see today, from the Big Bang to the vast space filled with galaxies, stars, planets, and life, unites us all. From the perspective of inhabitants of planet Earth, 2/3 of cosmic history passed before the appearance of the Sun and Earth. However, life emerged on our world as far back as we can peer into the past through measurements. It may have appeared even 4.4 billion years ago. This makes us wonder, did life arise in the universe earlier than on our planet? How long ago might it have emerged? To be more precise, how soon after the Big Bang could enough heavy elements accumulate to form planets and, possibly, life? The answer to this question takes us further into the past than we could ever imagine. Graphite deposits have been discovered in zirconium, which is the oldest evidence of carbon-based life on Earth. The amount of carbon-12 found in these deposits dates the emergence of life on Earth to over 4 billion years ago. Of course, we cannot travel back to the very beginning of the universe, because after the Big Bang, there were not only no stars or galaxies, there were not even any atoms. Everything takes time to come into existence, and the universe, after giving birth to matter and antimatter, started from a fairly homogeneous state. The densest regions comprised only a small fraction, possibly as small as 0.3%, denser than the average. This means it would take an enormous amount of time for gravitational collapse to work on creating, for example, planets that are much denser than the average density of the universe. Yet, the universe had enough time for all of this to come into existence. If we look at the standard timeline of the universe's history, Earth appeared only after 9.2 billion years after the Big Bang, but many of the steps necessary for creating a world like ours happened very early on, just after 1 second. Antimatter annihilated with the majority of matter, leaving a small amount of protons, neutrons, and electrons. A sea of neutrinos formed, and after about 3 to 4 minutes, protons and neutrons combined to form neutral atomic nuclei, but most of these were isotopes of hydrogen and helium. Only when the universe cooled down to a certain temperature, which took approximately 380,000 years, did electrons join these nuclei, forming neutral atoms. However, even with these fundamental ingredients, life and rocky planets were still impossible because cooling the universe meant that atomic nuclei formed, followed by neutral atoms. Yet, practically all of these atoms were hydrogen and helium. Only much later did the heavy elements necessary for the formation of rocky planets and life begin to form. But gravitational collapse is a reality. Given enough time, it will change the face of the universe. At first, it progresses very slowly, but it gains momentum as regions of space become denser. The denser the region becomes, the better it is at attracting more and more matter, and the areas that start with the highest density grow faster than others. Our simulations show that the very first stars should have formed approximately 50 to 100 years after the Big Bang. These stars should have consisted solely of hydrogen and helium, and could grow to quite large masses, hundreds or even thousands of times the mass of the Sun. When such a massive star forms, it dies within 1 to 2 million years, but in the moment of its death, something remarkable happens, all thanks to its life. All stars synthesize helium from hydrogen in their cores, but the most massive ones not only synthesize carbon from helium, they also progress to oxygen, neon, magnesium, silicon, sulfur, and so on, following the periodic table of elements until they reach iron, nickel, and cobalt. After this, there's nowhere else to go, and the core collapses. This triggers a supernova explosion. These explosions eject a vast amount of heavy elements into the universe, giving rise to new generations of stars and enriching the interstellar space. The increase in the proportion of heavy elements signifies an increase in the number of rocky planets with high density and the quantity of elements necessary for life as we know it. We don't need the average stellar system in the universe to resemble our solar system. We only need a few generations of stars to live and die in the densest regions of space to replicate conditions suitable for the emergence of rocky planets and organic molecules. For instance, in the remnants of a supernova, there exists a slowly rotating neutron star, formerly a massive star that reached the end of its life. Although supernovae can send the synthesized heavy elements back into the universe, it's the subsequent mergers of neutron stars that create most of the heaviest elements. By the time the universe reaches just 1 billion years old, the most distant objects are abundant in heavy elements, as confirmed by our measurements. There is a significant amount of carbon, as much as in our solar system, and other heavy elements accumulate even faster than carbon. It may take more time to achieve a high concentration because carbon primarily emerges in stars that do not become supernovae themselves. However, Carbon is not essential for rocky planets, and other heavy elements also start to accumulate more rapidly. Possibly within several 100 million years after the ignition of the first stars, around 300 to 500 million years after the Big Bang, the most enriched stars have already formed rocky planets. This is seen in the protoplanetary disks around young stars. Gaps in these disks indicate the presence of new planets. As soon as the disk has a sufficient amount of heavy elements, rocky planets can emerge within it. If carbon were not essential for life, similar processes could begin in different regions of the cosmos. However, for life similar to ours, carbon is crucial, which means that the appearance of life may need to wait much longer. Even though carbon atoms will appear in the mix, it will take approximately 1.5 billion years for there to be enough of it. This period is before the universe reaches 10% of its current age. However, it's not just the 5% required for the formation of rocky planets. It's interesting to consider that the universe has formed planets and all necessary ingredients in the right quantities for life to emerge, except for carbon. To create a sufficient amount of this essential ingredient for life, we must wait until the most massive sun-like stars live and die. You see the remnants of supernovae on the left and a planetary nebula on the right. Both of these mechanisms allow stars to return burnt heavy elements to interstellar space, utilizing them for the emergence of stars and planets in the next generation. Sun-like stars, after their death, leave behind planetary nebulae, which are the primary source of carbon in the universe. It takes more time for the production of carbon because stars that give rise to planetary nebulae have longer lifespans than those that perish in supernova. Extrapolating that back into the past, the most advanced forms of life that appeared on Earth in different epochs suggest an interesting exercise. It turns out that the increase in genome complexity follows a certain trend. If we go back to individual paired bases, the time frame suggests something more like 9 to 10 billion years, rather than the 12 to 13 billion years ago the Earth formed. This indicates that life could have emerged a billion years ago. However, in our cosmic region, it took several additional billion years to initiate. On this semi-logarithmic graph, the complexity of organisms, measured by the length of non-redundant DNA relative to the functionally non-redundant DNA, with respect to gene readability through paired nucleotides, linearly increases over time. We do not know this at the current moment. We do not know where the line between life and non-life is drawn. We also do not know if earthly life began here before other formed planets, or somewhere deep in interstellar space without any planets at all. Many amino acids not found in nature have been discovered in the Murchison meteorite, which fell to Earth in Australia in 1969. The fact that over 80 unique types of amino acids exist in a simple cosmic rock suggests that the ingredients for life, or even life itself, might have emerged through interactions on planets. It's intriguing, the elementary ingredients necessary for life appeared shortly after the formation of the first stars, and the most important ingredient is carbon. As the fourth most abundant element in the universe, carbon is the last ingredient to reach the necessary quantity for rocky planets. In some places, rocky planets appeared much earlier than life could have emerged, perhaps as soon as 500 million years after the Big Bang, or even earlier. However, once we have enough carbon, all the necessary steps for the emergence of organic molecules and the initiation of the direction towards life become inevitable. Whatever life processes led to the emergence of humanity, they might have begun when the universe was 10 times smaller than it is now. We can be certain that in our solar system, we are alone. The maximum possibility is the existence of some microbes. These would not be complex multicellular organisms. But where are the intelligent beings? If intelligent beings truly exist in the universe, their location is at least light years away from us. Two independent intelligent civilizations could coexist, excluding interstellar travel. If they followed a similar path as our life, the question arises, where are they? Perhaps we should start with the fact that to emerge, life must go through several stages, yet the ingredients for it are literally everywhere. Even if we limit ourselves to life chemically similar to ours, the universe is teeming with possibilities. Molecules capable of binding, including organic ones, are present both on planets and in space. This is the Omega Nebula, or the Messier 17 mission, an intensely active star-forming region, which explains its dusty and vivid appearance. Stars formed at different stages of cosmic evolution have different proportions of heavy elements. Although Earth formed over 9 billion years after the Big Bang, the universe didn't necessarily have to wait that long. Therefore, we'll categorize stars into 3 population types. The first population type includes Sun-like stars, which consist of 1 to 2% heavier elements than hydrogen and helium. They are composed of processed material, and their planetary systems have gas giants and rocky planets suitable for life. The second population type consists of older, ancient stars with only 0.1% of the heavy elements found in the Sun. Most of their worlds are gaseous and rarefied. They are too primitive and contain too few heavy elements for life to emerge. The third population type includes the earliest stars in the universe, which should be almost entirely free of heavy elements. The study of the earliest galaxies indicates that they are mainly composed of stars from the second population type. However, closer to us, there is a mix of young and old stars, rich and poor in metals. In star distances, the scale is accurate in this illustration, but if the picture were to scale, even the largest stars would be smaller than 1/1,000,000th of a pixel. One of the most important lessons for astronomers came from the Kepler mission when examining the Kepler 4444 system. This first population-type star has planets, but they are much older than our Earth. Our planet is only 4.5 billion years old, while the Kepler 444 system is 11.2 billion years old. This means the universe could have formed Earth-like worlds very early, at least 7 billion years before Earth appeared. Considering this possibility and the fact that regions like the center of our galaxy got enriched with metals faster and more significantly than our surroundings, it's quite possible that there are places in the universe, maybe even in our Milky Way, more conducive to the emergence of intelligent life than the Sun-Earth system. Given all that we know about the positioning of stars well suited for the birth of life, let's consider 5 main possibilities. This is the imagination of an artist regarding the TRAPPIST system, with its planets reflecting light from their surfaces. The potential presence of water on each of these worlds is depicted through seas, ponds, and vapor. However, it's unknown if any of these worlds have an atmosphere or if their parent star blew it away. One thing is clear. Potentially habitable worlds are located close to each other at a distance of only 1 million kilometers. In the early days of the solar system, it's likely that Venus, Earth, and Mars, and perhaps even Theia, a hypothetical planet that collided with Earth, had conditions equally suitable for life. Their atmospheres were filled with life-building ingredients, and there was liquid water on their surfaces. Venus and Mars at distances close to Earth's mark, a trajectory that spanned tens of millions of kilometers. However, around a Class M star, a red dwarf, planets could be separated by distances much smaller, as seen in systems like TRAPPIST-1. Potential habitable worlds could be as close as 1 million kilometers apart. Twin moons or planets orbiting a giant world, or a binary planet, could be even closer to each other. If life successfully emerged under certain conditions, why not have it arise twice, almost in the same place? This is a globular cluster, Omega Centauri captured using a powerful telescope. Globular clusters are massive collections of hundreds of thousands of stars, forming a spherical shape with a diameter of a few tens of light years. In the outer edges, the typical star-to-star distance is about a light year, but in the denser inner regions of these star clusters, stars can be as close as the Sun and the Kuiper Belt. Orbits in these star systems must remain stable, even in such crowded surroundings. Considering what we know about globular clusters, which appeared much earlier than the Kepler 4444 system, there should be promising candidates for life and habitability within a few hundred astronomical units. Although this distance changes over time due to star motion, you could call this an incredibly close encounter of 2 civilizations. This high-resolution image operates very close to the infrared range. Such pictures allowed us to discover 3 superstar clusters in the galactic center. Since long-wave light near infrared penetrates the dense dust between Earth and the galactic center, we could observe these superstar clusters. This cluster is from the central parsec, and all stars in these clusters, as well as the galactic center, are quite young. The closer you get to the galactic center, the denser the stars are. In a few light years from the center, star density is extremely high, much greater than the center of a globular cluster. In a sense, the galactic center is an even denser environment with massive black holes and extremely massive stars and clusters forming. While globular clusters lack these, there is a problem with those stars in the sense that we see them in the Milky Way's core. They are relatively young, possibly due to high variability in their local environment. Stars rarely survive there for even 1 billion years, despite the high density. In this area, stars come in different sizes, colors, and masses, including many bright blue stars, which are dozens or even hundreds of times more massive than the Sun. This is evident in the scattered star cluster NGC 3766. So, let's consider the existence of a civilization in a densely packed star cluster, or a spiral arm. Spiral arms are rich in unusual regions of the galaxy, where young stars are more likely to form from these epochs. Star clusters often contain thousands of stars within a region just a few light years in size. However, stars don't remain in such a configuration for very long. A typical open star cluster disperses in just a few million years, and only a small fraction of them survive for billions of years. Stars constantly enter and exit spiral arms, including our Sun. In summary, while the typical distances between stars within a cluster may be around 1 light year, they are unlikely candidates as the cradle of life. This logarithmic diagram displays distances, showing the Voyager spacecraft, our solar system, and the nearest star. So, let's consider the latest idea that everything is distributed in interstellar space. In other cases, stars end up in the same situation we observe, distances between them being on the order of a few light years. Approaching the center of the galaxy, we can reduce this distance to what is encountered in open clusters, approximately 1 light year. But if we get too close, we face the problems we see in the galactic center: mergers, interactions, and other catastrophic events that are more likely to interfere. To maintain a stable environment, we can reduce the distance, but the typical interstellar space is not suitable for this. If we adjust for close encounters, the best approach would be to wait until another star passes close to the initial one. With a typical star, this happens approximately once every million years. This graph represents the probability of a star passing at a specific distance from the Sun, with both axes being logarithmic. While we don't expect intelligent extraterrestrial life to be a frequent phenomenon in the universe, as common as planets and stars, every world that meets the necessary conditions represents a chance. Each time you get a chance, you gain an opportunity for success, with a finite probability. Each of these possibilities may turn out to be reality, but until we venture there and see what is there and what isn't, it is essential to objectively assess what kind of extraterrestrial intelligence the universe may provide us. The truth is somewhere out there, but it's important to understand that if we were extremely lucky, it could be much closer than we dare to imagine today. Humanity is astonishing with its capabilities and continues to prove that nothing is impossible for it. It is interesting to find out what lies at the bottom of the ocean and beyond the Earth's atmosphere. We create specialized research devices for this purpose. Space on our home planet is limited, but we can create artificial islands. But what can we do if the population reaches a point where Earth becomes overcrowded for all of us? Of course, we can search for planets with optimal conditions for life in other galaxies, and that seems like the most obvious option. But what if we create our own planets in the habitable zone of our solar system? It may sound too fantastic to some, but science has something to say about this. What would such a system with multiple planets look like? How many objects can it accommodate? Can there be more than one planet on a single orbit? And can all the components of such a system revolve around one central object? Before we delve into discussions about our ideal system with multiple planets, let's talk briefly about the current situation with the solar system. While we know about a vast number of planets outside the solar system, currently around 5,000, within the solar system, there are 8 planets. It's worth noting that our system holds the record for the most planets. We know about the TRAPPIST-1 system, which has 7 planets, and the Kepler-90 system, also with 8 planets. These two systems share other characteristics as well. The more massive planets are located farther from the main star, while the smaller ones are closer. Additionally, both systems have Sun-like main stars. However, there is one important difference in the Kepler-90 system. All the planets are located within 1 astronomical unit from their star, which means they are even closer to their star than Earth is to the Sun. And this is the 3rd planet out of the 8 in total. From this, we conclude that the density in the Kepler-90 system is significantly higher, which means it is possible to create a situation where the distance between planets is smaller than in the solar system. Next, it is important to understand if there is anywhere in the universe a system where there can be more than 1 planet in the habitable zone. In our planetary system, we have Earth, the only planet with optimal conditions for life during the early stages of the solar system's development. Venus and Mars, which are close to the habitable zone or even within it, could also have been suitable for life. We can take the TRAPPIST-1 system as an example, which contains 3 planets in its habitable zone. Scientists speculate that there may be systems with even 7 planets in the habitable zone. And what about having multiple planets in one orbit? We may not even be limited just 2 planets. There could be more. It is worth noting that 2 Lagrange points, L4 and L5, have a high level of stability in the Sun-Jupiter system. These Lagrange points are occupied by Trojan asteroids, which are located approximately equidistant from the Sun and Jupiter. In theory, not only Trojan asteroids but also Trojan planets could exist, whose positions would practically coincide with these mentioned points. However, such planets have not yet been discovered in the vastness of the universe. We have discussed planets that can form naturally in the universe, but now we will talk about creating systems with the maximum possible number of planets. We can rely on the work of astrophysicist Sean Raymond from the Bordeaux Observatory, who conducted research on this topic. Although his work is not licensed or published in scientific journals, we can extract some relevant information from it. We know that the density of systems similar to the solar system can be an order of magnitude higher. The maximum density value for further discussions will be determined. We will often use the terms sphere or radius in our reasoning. This refers to the space around a celestial body where its gravitational influence dominates. In other words, this space determines the orbits of smaller bodies, despite the influence of a larger object around which the smaller body directly orbits. The Hill sphere is located between the L1 and L2 Lagrange points. For Earth, the value of the Hill sphere reaches 1.5 million kilometers. Since the Moon is about 400,000 kilometers away from its planet, we conclude that Earth's satellite is located within the Hill sphere. The value of the Hill sphere, as we can see, is quite large, and it can accommodate all 8 planets. However, at what distance between planets will the system exhibit stability in terms of interactions between planets? The interaction between planets is strengthened when one enters the Hill sphere of the other, respectively. Destructive processes such as collisions can occur between 2 objects. In the articles by Sean Raymond mentioned earlier, there are studies that state the distance between planets should be equivalent to 5 or 10 Hill spheres. This raises the question of how many planets could potentially fit within the habitable zone of our solar system. It is worth noting that we do not know its exact size. The habitable zone extends from 0.95 to 1.37 astronomical units from the Sun. Taking these calculations into account, Sean Raymond concluded that we could accommodate 6 planets within the habitable zone of our planetary system, where life could potentially exist. So what can we do to increase the number of these planets? It would be ideal to place at least 2 planets on one orbit, with one of them located at either the L4 or L5 Lagrange points. This way, we would have a total of 12 planets, and the system would remain stable. Moving forward, how can we further increase the number of planets based on materials from the journals Celestial Mechanics and Dynamical Astronomy? We conclude that more than 2 planets with equal masses can coexist on a single orbit provided that the distance between them is at least 12 Hill radii. The minimum number of planets on one orbit would be 7, similar to Earth's orbit. Under such conditions, we could have as many as 42 planets. As we recall, there can be 6 orbits within the habitable zone of the solar system. Could there be such a number of planets on each orbit? The mass of the planets does not significantly affect the distance between orbits. Therefore, if we place 42 planets on 6 orbits, we would have a total of 252 planets with optimal conditions for life. The spacing between orbits largely depends on the influence of one planet, specifically the planet that another planet from a different orbit comes under the influence of. Let's go even further and try to increase the number of planets. Here we need retrograde orbits. In the solar system, planets move along their orbits in one direction. If the distance between planets is relatively small, the planets on different orbits, including gravitationally, influence each other, leading to instability. If two planets stay close to each other for an extended period, the consequences can be serious. In such cases, it is better to isolate these two planets from each other so they spend less time in close proximity. How can we achieve this? We need these two bodies to move in their orbits in opposite directions, resulting in retrograde motion. By doing so, we not only reduce the gravitational influence of some planets on others, but also decrease the distance between the orbits. If we raise the stakes, so to speak, we might be able to form habitable planets outside the habitable zone. Our limit would be 1,000 astronomical units, based on the works of Sean Raymond. This is the optimal distance from the main star, as the external influence on planets will not be significant. Thus, within this zone, we can place 57 rings, each containing 42 habitable planets, resulting in a total of 294 objects. Even though such a quantity may seem incredible and extraordinary, it will not outweigh the total mass of the main star. The Sun will still be orders of magnitude more massive than all the objects in the system combined. Indeed, our reasoning is currently fantastic and purely theoretical. Of course, something like this cannot form in our solar system. However, over time, we may discover planetary systems similar to the ones we described. What do you think? Do you expect such discoveries in the future? And if so, how soon? On Saturn's moon Titan, there are both land and seas, as well as 6 elements that are abundant, so scientists believe that there is a high possibility of life on Titan. Let's take a closer look at the possibility of life on Titan. Titan, a moon of Saturn, is huge, second only to Ganymede in size among moons in the solar system. With a radius of about 2,575 kilometers, it is 1.5 times larger than the moon and about 40% the size of the Earth. Although it can be observed from Earth, it is difficult to observe Titan's interior properly because of its thick atmosphere. Therefore, Titan was a mysterious celestial body shrouded in mystery for a while. However, in 1997, the European Space Agency and NASA launched the Cassini spacecraft to explore Saturn and its moons, and this spacecraft visited Titan. Hundreds of photos and atmospheric composition analysis were sent to Earth, revealing its identity. The image of Titan sent by the Cassini spacecraft was quite ordinary, with mostly wide plains and sand dunes created by the wind in low-lying areas. There were even mountains as high as 3,330 meters. At first glance, these photos looked like hazy days on Earth with dust or fine dust. Clouds were also observed in the sky of Titan. Weather phenomena occurred on Titan similar to those on Earth, with rain falling and lakes forming on the plains, and even seas forming in low-lying areas. Like Earth, liquid circulation also occurs on Titan. With this information, it seems that the speculations of Professor Carl Sagan, who was always right about the possibility of life on Titan, were not true. Or perhaps humans on Earth will one day be able to live on Titan. Because it is located as far as 1.4 billion kilometers away from the Sun, it doesn't receive enough solar heat properly. So as it turns out, the average temperature of Titan is minus 179 degrees Celsius. Titan can be called a supergiant freezer. Normally, if the temperature is minus 179 degrees, all the clothes on this satellite should freeze. Clouds 3 and oceans confirmed through Cassini 5 have a significant discrepancy with what we usually know. The hills on Titan were formed by completely freezing, and the seas on Titan were made up of methane. Also, the clouds were not white clouds gathered by water vapor like Earth, but had a murky appearance. When we only saw Titan in photos, we thought it could be habitable, but it's definitely not a place with a climate like Earth. Even though our environment is like this, scientists' opinions were very positive when Titan was discovered, except for Earth, as it is the only place where liquid is maintained on the surface in a stable way. This is the first celestial body that we confirmed, and there might be life forms here. Also, thanks to the layered structure of Titan, there are winds and rain, making it an optimal place for life. Now let's take a closer look at Titan. Titan has a dense, murky atmosphere. The atmospheric pressure is about 1.45 times that of Earth, and about 98% of the atmosphere is made up of nitrogen with trace amounts of methane. Interestingly, aside from Earth, Titan is the only celestial body in the solar system with nitrogen. Scientists say that Titan's nitrogen-rich atmosphere is very similar to the primitive atmosphere of Earth about 3.8 billion years ago. If we can analyze Titan's atmosphere, we can learn more about the changes in Earth's atmosphere. Currently, nitrogen is the most abundant gas in Earth's atmosphere, accounting for 78%, followed by oxygen at 21% and argon at 0.90%. These atmospheric compositions are present on Earth. However, these ratios have changed slightly over the course of several hundred million to billions of years. Titan's dense nitrogen atmosphere causes a greenhouse effect, which maintains a high temperature despite receiving very little solar radiation. This keeps methane in a liquid and gaseous state. If Titan did not have nitrogen, all of its methane would have frozen, and Titan itself would have become a completely frozen celestial body. Amazingly, the study of Titan has even led to the discovery of some unique molecules that are essential for life formation, such as cyclopropanyl, which is composed of carbon and 2 hydrogen atoms. This molecule is an important building block for life and also serves as food for other organisms. Although cyclopropanyl is difficult to pronounce and understand, it is a crucial substance that cannot be overlooked in the formation of life in the universe, and has been observed occasionally in interstellar matter. However, except for Titan, there has been no discovery of such compounds in other celestial bodies, so it's really amazing and remarkable. Cyclopropanyl, composed of 2 carbon atoms and 2 hydrogen atoms, has been discovered in Titan's atmosphere using the ALMA radio telescope by NASA's research team. The discovery of this molecule, which is difficult to pronounce and has caused quite a stir, is an essential component of the formation of living organisms and can also serve as food for other organisms. Although it has occasionally been observed among interstellar substances in the universe, it has never been found in any other celestial body until now, except for Titan. This is really remarkable, especially considering that it has only been found in 2 places, Titan, which is similar to the primitive Earth environment, and some other celestial body. Moreover, many benzene compounds have also been detected. These compounds play a role in the formation of complex organic matter. In addition, there are other compounds such as argon and carbon monoxide in the atmosphere of Titan, which is conducive to the formation of organic matter during its evolution. It is an environment where organic matter formed during its evolution is falling like light snow. There is one more fact to note about Titan. It is that 82% of its surface is covered with organic matter. According to Dr. Rosalie Lopez, a NASA scientist, more than 82% of Titan's surface is composed of organic matter that has fallen from its atmosphere and has been transported by winds. This means that Titan's organic matter is very abundant, which suggests the possibility of the existence of living organisms. This is an exciting discovery that raises the possibility of the existence of microbial or other life forms. If such life forms were present, there would be abundant sources of food. Another important fact is that there are oceans on Titan. Prior to this, lakes were discovered on Titan, but now it has been revealed that there are oceans as well. If the liquid in these oceans seeps into the subsurface, it could provide sufficient conditions for the birth of life. While this liquid is not water, Titan is the only celestial body in our solar system besides Earth, where liquid exists on the surface. Scientists have found that Titan's oceans are deeper than previously thought. In fact, during an investigation of one of Titan's seas, Kraken Mare, the equipment that was used to probe the sea was limited by its technological capabilities and was unable to reach the bottom, which is at least 300 meters deep. This is more than 7 times deeper than the average depth of the West Sea, which is approximately 43 meters. In addition, there are geological activities like volcanic activities in Titan, and if such visual activities occur, an ecosystem ranging from microorganisms that use organic matter around the hot springs as food to predators on top of them may have formed. From the beginning, including Titan, organic matter is very abundant, so if miraculously some organisms were discovered on Titan, an ecosystem of organisms and their mothers could have already formed in Titan's seas. The most important clue is this. Recently, it was found that after hydrogen descends from Titan's atmosphere, it disappears from the surface, according to the data collected by Cassini. Some scientists at JPL are claiming that this may be the result of primitive life breathing in and consuming material on the surface. However, Titan's flowing liquid is methane, so if life is actually emerging and surviving here on Titan, the living organisms of Titan may be based on methane. Scientists are looking at Titan's existence of life with a very positive outlook. NASA has started the Dragonfly project to explore the seas of Titan. They will fly a kind of drone powered by a blue-tone fuel to observe various terrains of Titan. The Dragonfly project is expected to launch in 2026 and arrive near Saturn in 2034. They plan to use a parachute to land on Titan when the weather is favorable, and then switch to flight mode to explore and collect samples. Previously, Genius explorations were mostly conducted using ground vehicles, but this method had limitations in mobility, so the goal is to easily explore multiple locations. I will go crazy with my child's drone to explore. The target distance and time for the exploration are about 2 years, 7 months, and approximately 175 kilometers. This distance is twice the distance traveled by all Mars rovers so far. NASA hasn't made a final decision yet, but they say they could send a 1-ton submarine to Titan. The purpose would be to explore the largest Kraken Mare Sea on Titan, which has a fairly deep depth from the beginning. A submarine would be 10 times better than a drone to explore it. If we explore the liquid methane ocean with a submarine, we could thoroughly examine the ocean floor. What do you think about the possibility of life on Titan, Saturn's moon? Scientists studying space believe that there must be life forms somewhere other than Earth. With the era of space exploration in full swing, humanity is searching for traces of life within our solar system. Among the many planets, the most likely place to find life is Mars. So why do scientists believe that there is a high possibility of life on Mars? In the late 19th century, astronomers observed Mars through telescopes and discovered that it rotates on its axis and its tilt is similar to Earth's. They also observed that Mars had seasons, which indicated that Mars has an atmosphere similar to Earth. These observations suggested that Mars is like a second Earth with its own unique features. In addition, in 1877, Mars moons Phobos and Deimos were discovered, further increasing interest in Mars. Since then, scientists have continued to observe Mars and have found evidence of water on its surface, leading to the possibility of the existence of life on the planet. I discovered that some areas of the surface were bright, while others were dark, and at the time, scholars believed these to be continents. They also thought that Mars had a dense atmosphere, and when they continued to observe Mars, they believed that the changing colors on the surface were due to the seasonal changes of plants on Mars. In October 1895, the American astronomer Percival Lowell made the following claim. "Through my telescope, I have watched Mars for a long time, and I am sure that there are canals made by Martians, and on the planet there is a civilization and Martians live in society." In the 18th century and early 19th century, scientists had debated whether or not there was evidence of life on Mars. However, as humanity's space technology rapidly advanced, some scientists began to argue that we should go to Mars to find out firsthand. The first country to attempt to explore Mars was the Soviet Union in the 1960s, but they experienced many failures. Starting from the atmosphere, now the US is starting its exploration of Mars. Oh, the Thomas exploration is not an easy task. Oh, it's not some cheesy talk on a Friday night. But we're talking about the only light young king out there. Should we book a cell and go to Mars first? Although the Soviet Union started exploring Mars 4 years before the US did, the US was the first to achieve results. In 1965, the US's Mariner 4 became the first spacecraft to approach Mars closely and send back images to Earth. The photos taken at that time totaled 22, but since it was an era of black and white photography, the image quality was not very good. Then, in November 1971, the US's Mariner 9 became the first spacecraft to successfully enter Mars orbit and sent back an enormous amount of data to Earth, including only 9 photos out of 7,300 taken, capturing about 80% of the Martian surface. The photos taken are diverse, including impact craters, the largest volcano in the solar system, Olympus Mons, and the erosion and deposition that occurred, almost showing the entire Martian surface. During this time, the Soviet Union was also tirelessly pursuing Mars exploration, but they didn't achieve significant results. Now, the United States, with billions of dollars, is embarking on the ambitious Viking project, focused on searching for extraterrestrial life. After the successful landing in 1980, Mars became a utopia. They successfully landed on the plains and immediately transmitted nearly 16,000 images back to Earth. In 1976, Viking 1 and Viking 2 successfully landed on Mars. After landing, they began searching for signs of life on Mars. They collected samples from the Martian surface and analyzed the atmosphere, but they couldn't find any trace of organic matter. However, the Viking lander had a fatal problem of being unable to move after landing. With all the exploration they're doing on Mars, it seems like they won't be satisfied with just one purpose. For the Mars exploration, NASA sent a rover with 6 wheels to actively explore various places. That's how the Mars Pathfinder was launched, with the intention of exploring multiple locations. The Pathfinder landed on Mars in July 1997. The Sojourner rover traveled around various locations on Mars for about 3 months, researching the atmosphere, soil, and rocks in search of life forms. However, once again, they did not find any friends of any life forms. Nevertheless, there were still significant achievements. It was revealed that the Homestake event occurred about 3 million years ago, causing erosion that created the Ares Vallis. This means that our existence on Mars had an impact. After the success of the Mars Pathfinder, humanity continued to send exploration missions to Mars. The goal is to explore Mars itself or find evidence of water or life on Mars. First, Mars Odyssey found evidence of water and ice on the surface of Mars from orbit. In 2003, the European Space Agency's Mars Express mission discovered water molecules at the south pole of Mars and succeeded in capturing images of ice. In 2008, NASA's Phoenix mission landed at the Martian North Pole, where it found water and ice and collected samples from the surface. The purpose of studying these Martian samples is to determine whether there is life on Mars or whether it could support life. Next, the Q-City mission discovered that methane levels on Mars vary significantly with the seasons. On Earth, methane is mostly produced by animal waste or the decay of organic matter. Therefore, methane is a powerful indicator of life. Of course, methane could also be produced geologically. Currently, researchers are actively studying where this methane comes from and whether it is produced geologically or by living organisms. Humans have sent dozens of Mars probes so far, but we have never found any signs of life or even traces of it. Why is there no life on Mars? First of all, it is very unlikely for Mars to be habitable. Its mass is only 1/10 that of Earth, and its gravity is only 1/3 that of Earth's. If a 70 kilograms person goes to Mars, their weight would become only 26 kilograms. Because of the weak gravity, Mars cannot hold on to its atmosphere, which gradually escapes into space. Second, Mars is much colder than Earth, and its magnetic field is very weak, only 1/80/100 of Earth's. With such a weak magnetic field, Mars cannot block the solar wind, which causes the atmosphere to disappear. As a result, there is hardly any air on Mars. Of course, Mars has some potential for becoming habitable, and we are actively researching whether there is any microbial life on the planet, or whether it could support life in the future. Earth-like, Mars has carbon dioxide and water vapor in its atmosphere, and even oxygen. However, the atmospheric pressure on the Martian surface is only about 0.006 times that of Earth's surface pressure, which is only 0.75%. With such thin air, it would be impossible for any living organism to survive. Compared to the Earth's environment, the Martian atmosphere is almost like a vacuum. This thin atmosphere also lowers the boiling point of water on Mars. The boiling point of water on Mars is only 27 degrees Celsius, so if humans were to be exposed to Mars's atmosphere, the water inside their bodies could be sucked out. It's really amazing. Another interesting fact is that the boiling point is the temperature at which the vapor pressure of a liquid equals the external pressure. If the external pressure decreases, the vapor pressure also decreases, so the boiling point decreases as well. In such an environment, even the most resilient organisms that are said to have high human survivability would find it very difficult to survive for an extended period of time. Mars also has extremely harsh temperatures. The average temperature on Mars is minus 80 degrees Celsius, and the surface temperature can drop as low as minus 140 degrees Celsius and rise up to 20 degrees Celsius. This temperature fluctuation is due to the thinness of the Martian atmosphere, which means that the molecules that make up the atmosphere are narrow and have less kinetic energy to maintain temperature and heat. This is why scientists have come to the conclusion that there is a very high likelihood that there is no life on Mars, as they have been studying the planet's physical characteristics since the 1960s, when they began sending Mars exploration probes. Today's video discusses the process of exploring life on Mars by our Parliament, and why scientists have determined that the possibility of life on Mars is very low. However, there are some who still insist that humans must colonize Mars despite its harsh environment, and one such person is Elon Musk of SpaceX.